I'm going to be talking about deep learning for extreme weather detection. But before we get to the main topic, I think given the theme from other speakers, I just want to briefly talk about what DOE is. It's a different national lab and what the NERSC Supercomputing Center does. So we at NERSC are the mission HPC facility for the DOE Office of Science, and there are a range of different domain science areas that we support. Probably what's most relevant to this crowd is that the Biological and Environmental Research Group, which does climate science in the DOE, we support their computing requirements. And then we, of course, run the big supercomputing centers. So the teraflop, the petaflop, and now the exaflop missions are owned by the DOE. So we are in the business of setting up big machines. There's a very strong applied math program in the DOE that develops PDE solvers, which are, of course, routinely used by climate scientists. One thing that's worth noting about NERSC is that we have a really, really broad user base. So we have about 7,500 different users, 700 different projects, 700 different code bases. So creating a single unified system that can support both simulation and data analytics workloads is quite a challenge. So that's one of the challenges that I have personally. This is our machine room right now. So there are two supercomputers. Both of them are Cray at this point in time. Cori is our flagship system. It's a Cray XC40 system. It's about a 30 petaflop class machine, hundreds of terabytes of memory, tens of thousands of nodes. For data analytics and also for simulation, if you had a big job that you wanted to run, then you can use something called the burst buffer, which is a big SSD pool of memory that you can write and read data from. Amy sort of touched upon challenges pertaining to moving data in and out of machines. So one of the unique things that the DOE has is the Energy Sciences Network that connects all of the major national labs and facilities. Right now, we have 100 gigabit connections in production, but 400 gigabit connections are also being deployed. Now, frankly, the challenge in the data space in the last 2 or 3 years for us has been in determining the stack. And I think Brian touched upon some of the themes here. For 40 years, I think Doug chatted about 2 million lines of Fortran code. There's a huge legacy, but in some ways, I think the HPC community knows generally what programming languages there are, and we know how to support them. The vendors know how to support them. But correspondingly, what should be the stack in the data space has been a big question mark. A lot of technologies are coming in. Some of them are phasing out fast. So in the last 3 years, we've articulated that this is going to be the stack that we'll support at NERSC. So obviously, supporting data transfer is important. So I think maybe, Amy, your point was to the contrary in that data transfer is tough. But certainly, in NERSC, we have a centralized resource. And people do want to move data to a place like NERSC. So we do support tools like Globus and GridFTP. Those are commonly used in science. Once the data is in place, then chances are that a scientist will want to share that data set with the rest of their community. So it's not, the data is in a black hole or something. So there's a range of web portal technologies that we also support. I note that Jupyter wasn't touched upon so far by any of the speakers. So we do believe that going forward, the way you're going to be interacting with the supercomputing center is not going to be through command shells. It's likely going to be through a Jupyter notebook. So you just bring up the notebook. You can share it with the rest of your colleagues, and there's going to be a magic run on an HPC system button that will take all of the implementation details of launching jobs and so on and so forth into account. Now, workflows are important because if you have a certain analysis that you want to run on hundreds of data sets, you're not going to be doing it by hand. So automated workflows that take into account job failure, automatic restart, that's extremely important. So we have a range of homegrown technologies that we support right now. Now, Brian, I think, did a really good job in alluding to the challenges of data management. So for the climate science community, NetCDF is really the key file format. But underneath NetCDF right now, HDF5 is the IO library that's important. So we do support HDF5. The particle physics community has used Root for a long time, so we support that as well. Now, if IO libraries aren't quite your thing and you want to store your data in a database, there's a range of other technologies you can use. A bunch of visualization tools in the DOE landscape that we've been supporting for the last 2 or 3 decades, so we do that. Now, frankly, I think a lot of the buzz in the data space is in data analytics. But I'll get to that in a moment, but you should not forget that data analytics is just a part of a bigger stack. So it's important to keep the entire ecosystem in mind. So in the data analytics space, Python, I think it used to be maybe 3 or 5 years ago when HPC folks used to laugh at Python saying, oh yeah, this is just it's never going to cut it. It's never going to run on a supercomputer. But frankly, this is the go-to language now for data science. So much of the challenge at supercomputing centers is to make sure that Python works well. And we work closely with Intel and Cray and other vendors in making sure that Python does a good job. Now, R is, of course, the lingua franca of statisticians. I mean, if you've been to grad school, chances are you know R. So we try to make sure that R works well. I think Spark was touched upon, so that's a different framework that's come about in recent years. Also, I think emerging languages like Julia are important. So we do support that at NERSC. Now, a bunch of legacy tools, I would say MATLAB, Mathematica, Fiji for image processing, but then certainly many other emerging technologies in deep learning. So tools like TensorFlow, Theano, Caffe, PyTorch are all important going forward. So at NERSC, in my day job, what I try to do is to make sure that this stack works well on our HPC machines, and you, the climate data analyst, or any other, really from any other domain science field, you get the best productive and performant experience on our existing HPC machines. Yes.
If you think about those tools that would work best across many cores, many nodes, which are your sort of favorites there?
Yeah, so right now, and Brian indirectly alluded to it. In Python, you do have a few options. So you can use Dask, you can use MPI for Pi to launch jobs across nodes. It's not going to scale beyond, say, tens of nodes. Python running on hundreds of nodes is a challenge at this point in time. But I think what we find is that people want to do throughput-oriented computing anyway, so it's okay. I think Python in that mode is okay. Spark can also run on tens of nodes, so that'll be just fine. We have certainly succeeded in scaling Julia out much harder. So we have run jobs in Julia that run on 9,000 nodes, and they seem to scale really fine. So yeah, and right now as we speak, we have TensorFlow running on 9,000 nodes. We have Caffe running on 9,000 nodes. These are deep learning frameworks that come from different communities. So Google is behind TensorFlow, and academic communities have been behind Theano. Berkeley has been behind Caffe. So. All right, so the talk is on deep learning, but before I guess I dive into deep learning, I think it's very important to appreciate that data analytics is a broad field, and there's immense amount of hype around deep learning. It doesn't mean that deep learning is going to replace every other analytics approach there is. So first, just for some context setting, there's general purpose AI. So self-learning intelligent systems that go around the world, sense things, decide what to do, perhaps become self-aware. Machine learning is a subset of AI, and then deep learning is a subset of machine learning. So you might have techniques like random forests and logistic regression, support vector machines that are in machine learning. But deep learning is a certain flavor, and I'll get to what deep learning specifically is in a moment. Now, obviously, statistics is the underpinning for all of these methods. So that's important to appreciate. Now, on the right side, again, this is how users approach things. So they might have graph analytics that they want to do. So there's a different set of tools that we provide. You have conventional image and signal processing that you might want to do in MATLAB. We support that. And then some people just want to do raw linear algebra. So they're familiar with LAPACK or BLAS, and that's important. So really, I think the point of this slide is that deep learning is enjoying a lot of success in a lot of areas, but at an HPC center, we need to support the entire portfolio of data analytics methods. All right, so I'm going to switch to my main talk now. So what I'm going to do chat about is deep learning for extreme weather detection. So I'll briefly motivate the scientific problem. Some of you may have been tracking how deep learning has been doing in computer vision, but just in case you haven't, I'll spend a few slides on trends and successes that have been observed so far. Then we'll switch to deep learning for climate science. So I'll talk about the results that we have so far, but then I'll also call out what the challenges are, and then speculate a little bit about the future of AI in climate science. All right, so for the rest of the talk, when I say extreme weather, this is what I mean. We have phenomena like hurricanes, hundreds of kilometers across, extratropical cyclones, which might be thousands of kilometers across, features like atmospheric rivers that transport a lot of moisture from the tropics, and if the atmospheric river makes landfall on the west coast of the US, a lot of precipitation happens, and then weather fronts. So these are the phenomena that we're going to be studying. The reason these are important is because they tend to have a lot of impact. So this is the aftermath of Hurricane Harvey in Houston. In 2017, the US was hit by 4 major Cat 4, Cat 5 storms. So this was a dramatic year for the US, essentially streets being turned into canals and so on. This is Hurricane Irma making landfall in the Caribbean. Now closer to California, California obtains about 50% of its precipitation through atmospheric rivers. It so happened one year that 3 atmospheric rivers in succession deposited a lot of rain in California. So this is the Orville Dam, and essentially the water levels exceeded what the dam could hold. So there's a lot of emergency channels that they had to open up in essentially that dam, which resulted in a lot of flooding downstream. So if you look at these events, hurricanes, atmospheric rivers, extratropical cyclones, the question we want to ask is how such extreme events are going to change in the future. And I think Brian was touching upon that towards the end of this talk, in that the conversation around climate change tends to be around, are we talking about a 1.5 degree increase or a 2 degree Celsius increase, or maybe a foot or 2 sea level rise? But people are starting to ask localized questions. Will Cat 4 and Cat 5 storms start making landfall more often in the US or less often? Once they make landfall, are they going to be more intense or are they going to be less intense? If you look at atmospheric rivers and precipitation, due to climate change, will the atmospheric river tracks start skipping California altogether and 50% of your precipitation disappears? So those are the kinds of questions you want to ask. So how can you possibly address this question? You can look back in time, so you can look at paleoclimate records, but typically the quality of such records is not very high. So really, the best solution here is to look forward in time. And the mechanism that you have there is to run climate simulations. And I think Doug touched upon that right in the beginning. So you can, modern climate models take into account internal climate system variability. You can plug in external forcings. You can plug in anthropogenic influence. So I guess in his talk, Doug talked about various carbon emission scenarios. You can plug those in and run your climate model out till the end of the century. So the challenge is, well, given that I have 100 years of data, how am I going to find extreme weather patterns in this large data set? So essentially what you need is an objective tool for detecting extremes. It should not be a subjective decision that you make. So it is a pattern detection task. I'll touch upon that in a moment. And the question is, given that deep learning is doing extremely well for pattern detection right now for commercial applications, how well can it do for climate science? All right, so Doug had an excellent movie right in the morning, but we have a slightly different model. This is the CAM5 quarter degree model. This is DOE's production workhorse. And the question you should be thinking about is, there are interesting patterns here. There are hurricanes that are forming. There are extratropical cyclones. There are atmospheric rivers. If I show you a movie that runs out for 100 years, how are you going to find these patterns automatically? Doing this by hand is pretty much impossible. Takes a lot of effort, and quickly I think you start hallucinating features and making mistakes. So you better have an objective tool that doesn't get tired, doesn't get subjective, is not biased, and it works consistently well.
What is an extreme event in there? I mean, it is
So-
a hurricane, or it is one of those with the streams hitting California?
Yeah, so in this particular movie, it's easier to make out hurricanes and some extratropical cyclones. These bands of water vapor. Yeah, and again, you as the climate scientist can decide on what extreme events you want to study. All right, so I'm going to take a digression into deep learning for computer vision now. In computer vision, maybe I should just ask: are there computer scientists in the audience, or if you're a computer scientist or a computer vision person? You can raise your hand. Okay, cool. So some of you are. So in the computer vision setting, the challenge is the following. I upload my favorite image from Google, typically consists of cats and dogs. And the task that you're interested in solving is a classification task, so maybe a binary classification task. Given an image, does this image contain a cat or not? Yes or no? The localization task is, it's fine for you to tell me that there is a cat in the image, but I'd really like you to draw me a tight bounding box around the object of interest. Now, any complex image might have multiple objects, so multiple cats and dogs. So the detection problem is draw me different size bounding boxes around different objects. And finally, the segmentation task is bounding boxes aren't good enough. I'd really like a pixel level mask and tell me where cats and dogs are exactly. Now, deep learning has been successfully applied to solve all of these problems, essentially in recent years. This is the detection problem. Given real-world images, draw me a box around a bird or a frog. You'll note that these images are fairly complex. There are illumination conditions between the top two images is really quite different. The scale of objects is different. The point of view wherein you might be looking at is different. Some of the objects are occluded or you can only see them partially, and so on and so forth. Now, one of the important reasons why deep learning has come to the fore is the presence of this data set called the ImageNet Dataset. So Fei-Fei Li from Stanford and her grad students put together this data set with about 1.2 million training examples, probably more, and thousands of object classes. And then Jeff Hinton and his students in Toronto created an architecture which is now called the AlexNet Architecture. They fed in 1 million images and learned filters that would do best for this job, for the job of finding objects in images. Now, just very, very briefly, the way deep learning works is that you create this architecture. So you have an input image, say it's 224 by 224 by 3 channel image. And then you have a sequence of convolution and pooling operations. Convolution is the same thing that you have in image processing. Given an image and a filter, you just apply the filter. And then pooling is a nonlinearity that you typically impose. Now, the key difference in this approach as compared to 3-4 decades of computer vision is that Jeff Hinton and others decided to just give up on the notion that we knew what the best features were to specify. Let the deep learning system figure out what the features would be. So you have a random initialization of weights in this entire pipeline. You feed in an image. Now, this is training data, so you know what the label of the object is. You feed in an image, you filter it, so apply convolutions and pooling till you get to the end, and the network makes a prediction saying, I think there's a cat in this image. Now, chances are high that because you had a random weight initialization, you'll get junk prediction. You will likely make an error. So once you know, and you made an error because you had the ground truth for that data set, you compute the error, you take the partial derivative of that error with respect to the weights, and you update the weights. And essentially, you backprop the error through the entire network, tweaking your weights as you go along. Do this 1 million times, and you get a network that seems to work well. And probably one of the things that most amazed neuroscientists and probably even computer vision experts is that the filters that you get make sense. It makes sense compositionally. So the visualization of some of the filters that you see right in the beginning essentially correspond to Gabor functions, which is what the human visual system does. If you look at a visualization of weights in the intermediate layers, then you see texture patterns, which are compositions of simple Gabor functions. Move higher up in the network, you see object parts, which then in turn are combined to form objects. So this was really quite interesting, but really in the computer vision community, numbers are what matters, and there are the benchmark that people try to beat upon year after year used to be this ImageNet context. So in that particular context, so what's plotted in the y-axis is the error rate, so lower is better, and then along the x-axis are the best submission for the ImageNet contest from 2010 to 2016. So through 2011, if you could improve the error rate by 0.5% or 1/4%, that was a big deal. Suddenly, when Alex Krzyzewski and Jeff Hinton implemented this method, the error rate dropped dramatically. Since then, pretty much everyone in the computer vision community has given up on other methods and have exclusively jumped onto deep learning. And year after year, the error rate has gone down. We estimate that the human level performance for this task, this particular competition, is at maybe the 5% level. And now deep learning power systems have gone beyond that. So you can get superhuman classification accuracy using deep learning. This is not a one-off. Similar trends have been seen in speech recognition systems. You all have probably learned about the AlphaGo system and applications in self-driving cars as well. All right, so around 4 years ago, when when all of this was happening, I guess I asked myself the question, well, can deep learning work for climate science, given that it's working beautifully well for commercial applications? So there are similarities in deep learning for the industry, in that the kinds of tasks that we want to solve are similar. So we have a pattern classification task. We do have localization, detection, segmentation tasks. I'll show that to you visually in a moment. We do have some unsupervised tasks like clustering and feature learning. But there are some differences in climate data. In particular, we have multivariate data. So we typically don't have 8-bit RGB information. We have several dozen variables, which are typically high precision. The kinds of patterns that we are looking at have different spatio-temporal scales. And most importantly, the underlying statistics of patterns is quite different. So the way to think about it is, if you take your commodity camera, which might be a megapixel class camera, and you take images of the natural world, so in a million dimensional space, you now have a bunch of points corresponding to every image you've taken through your phone. In the ImageNet example, the job of the statistical algorithm or the machine learning algorithm is to learn hyperplanes that can separate cats from dogs in this million dimensional image, in this million dimensional space. In the climate science world, you roughly have a million grid points. That's your climate grid, let's say 2D for simplicity. Now, as your climate system evolves, you're populating a different million dimensional space. And now the question is going to be, can I learn hyperplanes that can separate out, say, tropical cyclones from atmospheric rivers and so on and so forth? So for a machine learning system, can it possibly operate in this regime of a different data set? That is the real challenge. Now, again, all of you know this, but if you take an image from the movie I just pointed out, and we just focus in on say, this tropical cyclone, there are several dozen variables one can look at. So wind fields, temperature fields, surface pressure, water vapor, so on and so forth. So this is fundamentally what the machine learning system is going to look at, and it'll need to operate on essentially this data set. All right, so hopefully that's enough of a background on what's happening in deep learning for computer vision. So we're going to now switch to deep learning for climate science. All right, so the analog basically is the following. So by now, hopefully, these images make sense to you. So finding cats and dogs in images. The problem that we're going to pose for the deep learning system is, given this multivariate spatial patch, is there, so we're going to formulate it as a binary classification problem, is there a tropical cyclone in this image or not? Yes or no? That's going to be the task. The localization task is going to be, draw me a tight bounding box around the tropical cyclone. The detection problem is going to be, given a global snapshot of the climate system, draw me bounding boxes of different sizes around tropical cyclones, a different colored bounding box around an ex-tropical cyclone, and a different colored bounding box around an atmospheric river. And the segmentation task is going to be, draw me pixel-accurate masks corresponding to these different features. So essentially what we've done over the last 3 years is to show that all of these problems as well can be solved with deep learning. And I'll try to skim through the results that we have so far.
Will you
Yes.
talk about how you use continuity and time?
So it's a good question. So right now we're treating, we're not taking time into account. So we are treating every image instantaneously.
So that's much harder.
So that's true in that adding temporal continuity should help you further improve the accuracy of your method. Now it so turns out that because deep learning is data intensive, you need a lot of data to feed these algorithms. And if a tropical cyclone, say, lasts 10 days, instead of having 10 examples of tropical cyclones, if you take a spatio-temporal version of the problem, that just boils down to a single example. So now you need to find many, many instances of whatever feature you want to train. Because essentially you'll change your deep net to take time into account through a convolution or through some other architecture, and that will almost certainly have more parameters, and you may not have that much more data. All right, so we're going to step through this one by one. So we're going to start with this binary classification task, and then we're going to end with segmentation. So again, the binary classification task, to keep it simple, we're going to crop around the feature of interest, no global images at this point. So it's going to be a crop-centered image. It's going to be a multivariate patch with labels. So that's going to be our training data. and then the job of the classifier is going to be to say yes or no. So just some specifics for tropical cyclones. We take image patches that are 32 by 32 in size. These are the variables that are being considered, and we have 10,000 positive and 10,000 negative examples. That's what we use for training. Sort of similar numbers for atmospheric rivers. All right, so this is the architecture that we end up using. Again, there's a little bit of tuning around which architecture to use, but this is the one that we end up using. So just a few convolutional layers followed by by pooling layers, and then one fully connected layer. Once you figure out what the right architecture is, get it to train, then sure enough, the performance of the DeepNet algorithm compared to other baseline methods like logistic regression, k-nearest neighbors, support vector machines, random forests is fairly good. Now, one observation here is that all of these numbers are fairly high. They are all 80% plus accuracy, which to me, I think, leads me to believe essentially that the climate science community may not has maybe not appreciated machine learning methods. Really, I think there are a range of methods that are available, and climate scientists or climate data analysts should start looking at machine learning methods. Now, certainly, I think it does look like deep learning is giving you state-of-the-art performance. Anyway, so this was the first test that we did, just to convince ourselves that deep learning could work on images of fluid flow data. So then we moved on to semi-supervised detection, which is, I really don't want to create separate networks for separate patterns, but I'd like to create one unified architecture to find all weather patterns. And I'd like that network to predict bounding box sizes. And also, and this is probably a holy grail problem, but I would like that network to find weather patterns for which I might have only a few labels or maybe no labels at all. So at NIPS last year, we published this semi-supervised architecture. And by the way, this is in collaboration with a number of people. I should mention that most of the results that I'm presenting have been done in collaboration with several folks. And for your reference, the names of the folks are listed below and their institutions as well. So for this semi-supervised architecture, essentially what we do is the following. So you start off with an image, and then you apply convolutions and pooling till you get to a certain compact representation of features, typically called the bottleneck layer. And then you ask the network in a supervised sense, so for the few patterns that you have labels for, in a supervised sense, you ask the network to predict bounding box sizes and the type of class or type of event. So far from left to the middle to the bottom, we essentially have a supervised classification problem. Now, this network does something else in addition, which is it also simultaneously takes this bottleneck layer and essentially does a deconvolution, or you can think of it as upsampling, and it creates an image that is of the same dimension as the input image. So simultaneously, the network tries to minimize predictive loss or error, and also to minimize reconstruction error. So again, once you've come up with the right architecture and gotten this thing to converge, which is may not be necessarily simple, but once you've gotten that to work, seems to work reasonably well. So on the left are panels of images of raw input fields, and on the right is what the network reconstructs. But fundamentally, detection is what we care about. So this is that same network looking at an image for which we know the held out ground truth in green, and then the network is predicting stuff in red. So in this case, for example, the green extratropical cyclone is here, and the network predicts the ETC in this location. Anyway, so it seems to be doing a reasonable job, but it's getting the scale wrong for features. It's not effectively able to search for the appropriate scale. But it is possible to train a single network to find 3 different types of patterns. Now, I mentioned this holy grail problem of potentially the network learning new patterns. So again, by no means have we solved that problem, but the approach, the conceptual idea is the following. The reconstruction works. For the supervised classification stuff, we know that the network can find 3 features. So all of the interesting parts are likely in this bottleneck layer. The bottleneck layer is where we've learned a compact representation of patterns. So using a tool called tsne, which is essentially a fancy version of doing clustering on this bottleneck layer, we essentially do the clustering, we superimpose patterns for which we have labels. And my hope was that all the blue stuff, so for example, tropical cyclones would be in a separate cluster, and the extratropical cyclones would be in a separate cluster, and the ARs would be in a separate cluster. And then you could ask the question of, well, what are these clusters for which we don't yet have labels? You can come in later on and introspect those. But the separation of clusters that we have right now is not as clean. So there's more work to do in this space. All right, so Brian alluded to this result. So this semi-supervised architecture that we have up and running is very demanding. So we train this on 15 terabytes of data, and if you try to do the training on a single GPU or a single node, it would really never converge. So you really need a big machine. So in this case, I guess, Brian, you got our numbers off by an order of magnitude, but we were running on 9,800 nodes. The entire Core supercomputer with 600,000 cores. And then you can get this training to work in tens of minutes. So there are some computer science details on exactly how you get deep nets to scale, but I can spare you the details, and we can come back to it later if you have questions. All right, so the binary classification stuff works. Object detection seems to be working reasonably. Segmentation is the next challenge. So again, there are classes. So first, the segmentation results that we are seeing from Facebook and other companies are looking spectacular at this point in time. So we've taken some of those architectures. It's called the tiramisu architecture. The details here are not important. Essentially, what happens is you take an input, you create a Laplacian pyramid, and then so that boils down the patterns to a compact representation, which then gets scaled out. There are some details around skip connections and so on and so forth, which really have to do with getting the networks to converge, which is not straightforward at this scale, but it can be done. So again, some details, hundreds of thousands of images. We are looking only at 4 channels for the time being. I'm going to come back to how we get ground truth in a moment, but there are some heuristics that we use to create ground truth. And the challenge really for the deep learning system is, given these segmentation masks based on heuristics, how well can it do? So on the left here is ground truth data as prescribed by heuristics. Stuff in black is the background, which is the uninteresting stuff. We don't care about that. Stuff in white are atmospheric rivers. Stuff in gray are tropical cyclones. And on the right is what the network learns and predicts. So generally, again, I mean, there are, as an engineer, I just jump to the problems first, but generally speaking, it seems to be getting the atmospheric river shapes right. And in fact, it seems to be doing a better job at finding atmospheric rivers than the ground truth data. The tropical cyclones, some of them it does get right, but there are false positives. So it's dreaming up tropical cyclones where there aren't. And there are some speckles in the data. So this is a noisy segmentation result, which we know how to get rid of, but that's what we have right now. So far, the segmentation results are looking promising. And just in case you're wondering why bother with segmentation, if you can segment out extreme weather events, so get pixel level masks, you can start doing analysis of the kinds of conditional precipitation. So right now, the way precipitation is typically handled is, you look at point-wise data, you look at point-wise time series. But breaking that out based on whatever cause it might be attributed to is not straightforward. If you can get pixel level tasks, if you can get pixel level masks, that becomes straightforward. You can essentially pull out all of the precipitation conditional on this. Then you can look at how precipitation conditional on tropical cyclones is going to change. Can the Clausius-Clapeyron relationship completely explain the expected changes in precipitation and so on? All right, so similar approach has been applied by Jim Beard and Ken Kunkel at NOAA. I think similar to what was maybe mentioned earlier, they actually have a data set wherein they've hand-labeled weather fronts, and it's taken a dozen people, I think 4 or 5 years to do that. So it's taken a lot of work to get these weather fronts. Even then, humans make mistakes. They get tired. They don't maybe want to care about labeling fronts over the oceans. They don't essentially mark fronts to completion, so on and so forth. So I'm going to show you a movie next where on the left is the ground truth. It's colored by various kinds of fronts, so warm fronts, cold fronts, and occluded fronts. And on the right is the output of the network. Once it starts playing. So in this case, again, the humans didn't care about labeling on the ocean, so that's okay. But as this movie proceeds, you're going to see that the labels which are being computed by the net are definitely more complete, and in some cases more accurate. So right now, Ken Kunkel and Jim Beard are doing a more careful analysis of some of these results and creating overall summary statistic, but also looking carefully at individual fronts and assessing their quality.
What's the time step there? Is that actual time?
It's probably days. So I think we have daily data for this data set.
Yeah, but it's not the algorithm iterating towards a solution. It's actual time.
Yeah, so there are individual, we're stepping through, say, Jan 1st, Jan 2nd, so on and so forth. There's ground truth data on this, and then the network's prediction on this. So it's not a visualization of the learning of the algorithm. All right. So next steps here. So so it's taken me, I think, 3 or 4 years to get convinced of this, but I do believe that deep learning can solve this problem. So what we're going to do is to think about a unified architecture for finding extreme weather phenomena in all data sets, segmentation, localization, detection, binary classification. It is really quite crucial. So, the name of the game in machine learning is training data. If you don't have training data, you're not going to be able to do machine learning. So what we are trying to do now is to come up with a schema and come up with a ground truth reference data set, which we can then in turn share with the climate community. And sharing the deep learning code base that has given us some of these results, we do intend to share that. Now, there's an important issue here around how the ground truth is obtained. So right now, for tropical cyclones, we use the best heuristic that exists, that comes from Kerry Emanuel in MIT. For atmospheric rivers, there's a slightly different heuristic that we use, and so on. So really, I think all we've done so far is to show that deep learning can match human heuristics. But if you think about what's happened in computer vision, the computer vision community has led researchers to believe that they should not be specifying heuristics at all. All they should be doing is looking at an image and saying yes or no, is there a pattern in this image? So what we'd like to get to is human experts providing data sets independent of heuristics. And as long as they can sign off on this data set, the deep learning system can take it from there. But getting access to such data sets is extremely hard. That is basically the problem going forward. Going back to your question, Doug, right now all of these are pretty much convolutional architectures that operate on single images. But extending that to time, we know is going to improve the accuracy of these methods even more. So there are architectures in deep learning called long short-term memory architectures that can take temporal evolution into account. So we are thinking about that. And Amy, I think on your question, so we looked at tropical cyclones, extropical cyclones, weather fronts, atmospheric rivers, but we do intend to extend this to Madden-Julian oscillation, different phases of the MJO, segmenting weather fronts in 3D, and then looking at blocking events. I'm sure there are other extreme weather events that people would care about. All right, so I did want to chat a little bit about challenges. So are we done? Not really. So for deep learning for extreme weather detection in climate, the challenges, what I would say is short-term challenges right now are around handling complex data. So all of our training and testing is done for a single model or an observational product. We never really switch resolutions, or we never do transfer learning. So train your network on a model output and then apply to an observational output that might be at a different resolution. So those issues are not characterized. It might be the case that some of the fields are present in, say, a simulation output, but then are missing in a satellite output. So will the network successfully or gracefully handle that? That's an open challenge. I mentioned the issue of accessing labeled data. So I think it's probably just a matter of time before the climate science community realizes that this is going to work, but really the gating step here is having enough labeled data. So I think that the community will need to come together and self-organize and run labeling campaigns to produce more data sets. And ClimateNet is one effort in that direction. Now, this challenge of hyperparameter optimization is a very important one. Essentially, what I mean by hyperparameter optimization is how do you decide on the network architecture to begin with? Should I use 3 convolution layers? Should I use 4 layers? Should I use an LSTM architecture? Should I use a 4D convolutional architecture? It's totally unclear. So this is really very few practitioners, deep learning practitioners, who really know how to tune these, and this is a challenge I think that the whole community faces at large. I touched upon performance and scaling. Right now in practice, if you have a single node, single GPU, single CPU, it's going to take you days and days to train your network on tens of gigabytes of data. And Brian and others, we already have tens of terabytes, if not petabytes of data. So for deep learning to work in practice, you have to solve the single node performance challenge, and you have to solve the scaling challenge. So in some ways, at NERSC, we're already working on this, but those tools need to be made available to the rest of the community. All right, so in many ways, I think these are engineering challenges, computer science challenges, social engineering challenges, which I think we'll just have to overcome. But really, there are some longer term issues around deep learning and its viability for science in general. So first, the way this field is evolving and the pace with which it's evolving is very, very empirical. So really, there's no careful characterization of what the limits are of supervised learning, unsupervised learning, and semi-supervised learning. How much data do you need? When should you apply one architecture versus another? GANs, I sort of shied away today. There was a question early on can you use deep learning to maybe make a surrogate model for an expensive, complex physics simulation. GANs, generative adversarial networks, are an architecture that you can employ for unto that end. But right now, the generalization properties of GANs are really not well characterized. It's a specific architecture that essentially learns a statistical model of your underlying data.
What's GAN stand for?
Sure, generative adversarial networks. So it comprises of 2 pieces. One piece learns how to produce realistic data, and the other piece learns to discriminate between real data and your fake synthetic data. All right. So anyway, so this needs a lot of work around more careful theoretical characterization of deep learning. But even then, I think interpretability is a big challenge. So right now, deep nets are complex and they are very black boxy in nature, and scientists are not comfortable with that. Effectively, I think we were just discussing this over dinner yesterday. The proposition that we are offering to climate scientists is, throw away 3 decades of throw away 2 to 3 decades of heuristics and replace it by a perfect black box. So some people are going to do that, but others are not going to be comfortable doing that. So I think there are a few approaches towards solving the interpretability problem. One is introspecting or visualizing or explaining a trained network. What are the activation functions that made the network behave behave the way it did? But the second approach is building in interpretability or building in known physics into the network. If I know that I'm looking at a fluid mechanics data set, there are some laws that this physical system subscribes to, conservation laws and so on and so forth. So can I build those in to my network? So hopefully the output that you get is going to be reasonable. Certainly, if people are going to be exploring GANs for synthetically generating physics, predicting the state of the system in the next time step and so on and so forth, you would need to incorporate physical consistency. You'll need to enforce that. And right now, there are no ways to enforce that. Uncertainty quantification, again in SAMC and in many other fields, UQ is a central theme, and UQ for deep learning is not yet fully developed. So we need that. Finally, I think this last point on really thinking about a methodology for applying deep learning, I think is really important. So if you think about how applied mathematicians approach computational modeling, they think about the natural system they're trying to study. They think about the underlying governing equations. They think about discretization schemes. They think about what solvers are guaranteed to converge on a certain discretization. They think about CFL conditions. They think about what spatiotemporal scales they're going to be able to resolve or not. And then they go ahead and implement the method, and then they scale it out. Compare that with what deep learning does right now. There's a certain system I want to understand. The protocol you have is, somehow you come up with an architecture, you turn the crank, and if it doesn't train, you either throw more data at the problem or you make the model more complex, and it's not very satisfying. So going forward, I think there will need to be a protocol around. I know that I'm studying a particular physical system. We will need to get to addressing some hard questions around how much data, how do I build in the physics, how do I tune the model, so on and so forth. All right. So I'm going to speculate a little bit about what maybe the future holds for AI in climate science. So if I look at the two communities, the computer vision community and how pattern detection problems have been solved in computer vision, and how pattern detection problems have been solved in climate science, there's been there's a lot I think that's happened in computer vision. So late 60s is when MIT developed neural nets. They also claimed they could solve computer vision problems in a summer, but it took them some time, I think, to move from simple neural nets to multi-layer perceptrons. A lot of the basic methods in backpropagation and so on and so forth were all sorted out in the 80s. But then other methods, random forests and later on SVMs, came to the fore, and I guess deep nets did not reach prime time. It's only in the 2010s when you had a large data set that was trained. You could then create a large network and then successfully run it because of GPUs and CPUs. You could actually run it and turn the crank on a laptop. That's when people really realized that deep nets could work. So anyway, so it's taken a bunch of time before deep nets have now been proved to work. Now compare that to how pattern detection problems are approached in climate science. In the computer vision community, I think there was a hope early on that using first principles geometry and physics and so on and so forth, you could really hand-tune features, and those would be the most informative and most relevant for computer vision, but that turned out not to be the case. I feel like we're still in this regime in climate science wherein we think that we know the climate system best. We think we know what the best description of features should be. So we still continue to rely on these heuristics, but I'm not sure how far that's going to take us. Now, certainly, thankfully, I would say there are specific targeted exercises like IMILAS. So that was an exercise wherein people try to compare different pattern detection algorithms for extratropical cyclones. A similar exercise is going on right now with atmospheric rivers. So that's great. I mean, I think these exercises will produce data sets that are curated. That's going to be important. So there is an analog here to what happened with the computer vision community. But I think from a philosophy perspective, I think what's been learned in the computer vision community is that hand tuning features doesn't quite work. So I think if we are willing to give up on that and produce a lot more labeled curated data sets, then there is a chance that we can jump on the deep learning bandwagon. All right, so I think what's going to happen shortly is that you're going to see deep learning tools being deployed at HPC centers and data centers. It's already happened in the cloud, and I do think that people will figure out how to get this to work. So it's likely that we will have finally maybe interactive analytics on fairly large data sets. I do think that this is coming, that the climate science community will produce data sets. I think that initially you're going to see researchers, this is already happening in high energy physics, but researchers are going to exploit a lot of low-hanging fruit, which is around, hey, I just completely solved this pattern classification problem, or regression problem is now solved. So that will likely happen. I think the engineering challenge around getting the networks to work on different modalities of data, simulation output, but also model output, and satellite and observational output, that's going to happen. I think the more interesting questions are what's next in the longer time frame. If you imagine for a moment that entire climate archives, so CMIP5, CMIP6, are all segmented and all classified, I think that then enables you to ask more sophisticated questions around correlation. So instead of doing analysis on pixel by pixel basis, now you start doing analysis on semantic objects. Tropical cyclones with respect to a certain phase of El Nino, so on and so forth. Potentially anomaly detection, we could think about that. And certainly I think causal analysis style problems are always going to be a grand challenge. But it's possible that the machinery that one applies for causal analysis can now start operating on semantically extracted entities. It's possible that in the longer term time frames, again, Google, Facebook, and others are definitely looking at some of these harder questions around interpretability and incorporating domain science principles and UQ and so on and so forth. So I think if we make some headway there, I do believe that these methods are going to be more broadly accepted by domain science community. But I think the question I'd like to leave you with is, if all of this happens, what is the value add of the climate data analyst? Is AI going to replace us? Are we going to be out of jobs? Not really. So I think what's likely going to happen is the following. So we have big supercomputers. Here's the one on Corey. We have deep learning software and other AI software that run seamlessly on these big machines. These machines will have easy access to observational data, simulation data. You solve classification, you solve segmentation, so it's easy for you to find patterns, clusters, maybe anomalies. There'll certainly be opportunities for the climate scientist, the climate data analyst, to do interactive exploration. Labels are an artifact of human language, so we certainly still expect humans to provide semantic labels and enforce conventions. But I do believe that in this context, where your workflow has become more seamless, the drudgery of moving data around, as Amy was alluding to, if that's gone through Jupyter notebooks, you can quickly tweak architectures. I think the climate scientist, the climate data analyst will be able to think more deeply about mechanisms and hypotheses. I mean, fundamentally, that is what they want to do. And right now, this workflow does not let you do that. So in many ways, I think AI is going to, and deep learning is going to make it easier for scientists to just focus on the big thing, which is mechanisms and hypotheses. All right, so just to conclude, I hope I've convinced you that extreme weather, understanding extreme weather is important. Essentially, finding extreme weather boils down to a pattern detection task that can be mapped easily to deep learning. We've effectively employed it so far for solving supervised classification, semi-supervised detection, and also now segmentation architectures. And going forward, we're looking at temporal variants of these architectures. I called out some short-term engineering challenges, which I think the computer scientists can likely help with. But also, I think we need the climate science community to step up and provide data sets. But there are certainly, I think, some longer-term challenges. I think, Richard, in terms of themes for joint SAMC ATI collaboration, I think these long-term challenges are sort of perfectly suited for this community to really help out with. And certainly, I think there's a lot of room for innovation and impact. Again, I say that the deep learning field is moving so fast that people don't wait for conferences anymore. I mean, they just publish stuff on archive and announce it on Twitter. So the field is moving extremely fast. So there's a lot of room, I think, right now for innovation and impact. And if any of these topics sound interesting to you, let me know. I'm open to collaborations. Please let Richard know if you're interested in collaborating in any way. All right, so just to call out again, this work was not done by me alone. There's a range of people in the industry and academia who've been contributing to this work. All right, thanks very much.
Okay, thank you.